Okay, so I think we will slowly get started with the next part of today's lectures. So we will talk about how can we really build the hardware now that we need to build these quantum key distribution and Bell tests that we talked about last time in the exercise. So the key idea is we will use photons. So photons are so-called particles of light. And I guess you all know light, since you're probably looking at it now, unless you have your eyes closed, you will see some light. But from a physics point of view, light, we think of it as really being electromagnetic fields. And when we talk about light in terms of quantum applications here, we often like to have what we call, with our technical terms, we call it coherent light sources. What that means in practice is we will have light at a single frequency traveling in a single direction. Sort of in practice, what you do is you build a laser, and that exactly gives that property of light. So you will have sort of a direction here where you will have light going through, and then the way electromagnetism works is that then the electric field will go sort of up and down as it travels along that direction, while the magnetic field will go parallel to that in that direction. And what we will do is we typically call the direction that the light travels into, we will call that the Z direction. And then the electric field could be sort of in any direction, but you can always think of it as sort of a linear combination of the X direction and the Y direction. So this is X, Y, or in between. And very often we sort of will only talk about the electric fields, because always the magnetic fields, if you are at least in vacuum, will be parallel to the electric field and completely out of phase with the electric field. So if you have described how the electric field travels through space, then you can also just calculate what is magnetic field. So typically we don't talk about this too much. So this is how we describe light, generally speaking. And what we're interested in is to figure out what is the smallest amount of light that you can have. And it turns out that when you go down to extremely small amount of light, it becomes discretized. That's part of the quantum mechanics description of the world. And the sort of smallest instance of that is what we call a photon. If you want to be slightly more formal about it, what really happens is that you can describe the energy of this as something like, now I will just forget all prefactors, but I will use out the electric field squared plus the magnetic field squared. Which is sort of similar to if you would have sort of x squared plus p squared, where x would be position and p would be momentum. And this you then know from as your harmonic oscillator that you solve in your quantum mechanics. So that would be a potential that would look like this, right? You would have x squared. And this would have sort of energy levels that go like this. So you could be in the state 0, which would have energy 1/2 h bar omega, where omega is the angular frequency of your harmonic oscillator. Then you would have the 1 state, which would be 1 plus 1/2 h bar omega, we'll have the 2 state, 2 plus 1/2 h bar omega, and so on. This is maybe a bit of a side, so don't think about this too much, but just to give you an idea how you should think about photons. Think about it as light really being an harmonic oscillator, and one photon corresponds to going from the 0 state, which we call vacuum, to the 1 state, where you have where you're in the eigenstate of a harmonic oscillator. That has the energy, which is h bar omega larger than your vacuum energy, which is this one. So this is why we think about photons, and what we have when we have that, we can then sort of move on and just think about it as a quantum mechanical particle. If you want to be slightly more mathy about it, we can sort of describe what I just showed on the previous slide in terms of a vector that looks like this. Sometimes we call this a Jones vector. It's not so important, but it is really just a vector that says that, okay, there's no electric field in the z direction, but there's some in the x direction and there's some in the y direction. Yeah, so field that goes in the x direction, this is the electric field that goes in the y direction. And you have this thing here, which means that it's a cosine when it goes along the z direction. It's like a light wave, and the wave moves in time. But you can think of it as a wave that just moves forward. Because we like to do calculations with this, it's actually easier if you write this as a sort of complex form. So you can essentially write it as this. So 0 e to the a z minus omega t plus 5x. And then you'll have e by 0 e to the I k z minus omega t plus 5y 0. So you can have it as a complex vector like this. And the only thing that we really need to know is that if you do it like this, it becomes much easier to do calculations with that, because exponents are easier to multiply or add together compared to cosines, as long as we remember that once we really want to know what we can measure, we have to take the real. Okay, that's fine. This we can do. And then we can have this complex description. If we take that and we can sort of take this kz minus omega t out of a parenthesis, right? Because it sort of goes into both. So we can write this like 0 e to the I. Sorry, I was the phi I wanted to write here. Phi x, and you have e y 0 e to the I phi y 0 times e to the I, and here you then get the kz minus omega t like this. Okay, so far nothing really very interesting happened here, but we can still make it somewhat simpler, right? Because we can also just remember that we are never in the z direction, right? So we can sort of ignore that part. And this part is sort of, we can just also keep in our head that it's there. So we can also, for now, ignore it. And then if we do that, we end up with sort of a very simplified description, which looks like this, which is just a two-dimensional vector like this. Yes, and now it starts to sort of already sound a little bit like a something we have seen before, right? But now this is a two-dimensional vector with complex numbers. And we can sort of go even a little bit further, right? because if we now say we have one photon, let's do the one photon assumption here, then we know that the energy is fixed. In other words, we have essentially that Ex squared plus Ey squared, that has to be a constant, right? So what we can do is we can essentially divide this thing with the total energy, or the energy which is this thing here. So we can have our 1 divided by, we can have our, let's call this E tot for convenience. Now E here is for energy, while this E is for electric field. Don't confuse it. So we have, essentially we can write this now as square root E tot. And then we can write some A here and some B here, times E to the I by X, E to the I by Y, where A is equal to E X divided by square root of E tot, and B is equal to E Y divided by square root of B E tot. And again, now we just have this constant factor in front, so we can forget about that. And this A, which is a real number, times this complex thing, means that we can have any complex number. So again, we can sort of rewrite this, and we get alpha, we get, which is a complex number, and we get beta, which is a complex number. And this is exactly how we would normally write our state alpha 0 plus beta 1. So what have we shown? So this might seems like a big detour, but essentially what we have now seen is that we have a single photon. That photon could either have electric field that goes in the Y direction or in the X direction. So essentially, if we would have electric field in the Y direction, then we would call that the state 1. An electric field that goes in the X direction, we call that the state 0. So we can really take a single photon, have it polarized in the X direction or polarized in the Y direction, and that is a qubit. This is a real way of making qubits. And this, and as you can see here, it sort of naturally follows from how we describe our electromagnetic fields. So this is that basic way of we can then travel information, because what we can then do is we can just prepare our qubit in a photon, send the photon through a fiber, and then measure the polarization at the end. And that's how we can transfer a qubit from one position to another. Does this make sense? Hopefully it makes a little bit of sense. But if there's questions, now is a good time to ask.
Sorry, this isn't so much a question. I can't see the bottom of the screen. For me, it cuts off right at where you have EX, A is equal to EX over square root of E tot.
Okay, that's a bit unfortunate. Let me then try to maybe do like this, and now everything up. Yeah,
yes, that's better.
Yeah. Now it doesn't look so nice with the predefined thing.
Yes.
But, yeah.
Okay, thanks. Sorry, what was the sum underneath the alpha beta? Oh no, that's just, never mind. I thought it was a sum.
Yeah, that's just me saying this is cool.
Okay. Oh, I may have to go into another view mode. Okay, I'll try that as well. Okay, yeah. Changing the view mode seems to have helped. All right, thank you.
Yes, then there's a question from Mo. So these prefactors that we keep ignoring, they're asking if that can be seen sort of as the equivalent of a global phase. And yes, exactly, that's what's going on. So what you see, for example, here is that there's sort of a global phase that depends on position and on time. So if you want to do sort of real measurements, you need to keep track of that global phase. But when we just describe sort of generic terms, you can just remember that we have this global phase here. And if you care about whether we are 1 or 0, it doesn't matter. Because then it's really just a global phase. And for the observables that we care about, it does not have an impact. Good. Any more questions for this part? Clear this drawing. And we move on to the next point. So now we have this description of light, and we want to know how can we really now measure our qubits, right? Because that's what we want to do. So we often talked about measuring, for example, sigma x or sigma y, but in the Bell test, for example, we also have this S and T operators that were slightly more complicated. And that's sort of a nice way you can do it when you have this description of light in this way, and that is you can take what we call a polarizing filter, and then just after it, we put a photon detector, just that when our qubit, which is really just a single photon, comes from the side, this whole thing corresponds to a specific measurement. Polarizing filters are essentially like a small piece of glass that lets only one polarization through, but blocks the other. And if you have been to a movie theater and watched a movie in 3D, the glasses on your 3D glasses are actually polarizing filters. They are not linear polarizing filters, but different polarizing filters, but it's sort of the same technology that goes into it. So it's something that's relatively easy to come by. Of course, if you want to do an advanced quantum experiments, you need to make them very high quality, but nonetheless, it's something you can relatively easily get. The same with a single photon detector. This you also have, specifically if you take your phone as a camera detects photons, right? So you really just need to put a camera here that is specifically tuned to just only measure the photons that comes through the polarizing filter. Have this set up. So it's really, compared to some other ways of doing quantum information, this is really very easy in terms of getting the hardware. It has some downside that I'm not going too much into, but in terms of conceptually building it, it's very easy. You can almost do it at home. So this is how you can build the measurement. So what do we actually measure here? So remember that we had our qubit state here, 0 plus alpha and beta 1, which we wrote at this vector here, alpha beta, where this was x polarized and this was Y polarized. So the way we can sort of describe this whole thing is essentially through the measurement matrix that we can write like this. So let's take the example here where maybe let's say that theta is equal to 0, which would correspond to the polarizing filter being in the x direction. So it will only let the photon through if it's in the 0 state. In that case, our M operator, so if cosine is of 0, that's 1, sine of 0, 0. So that becomes really just 1, 0, 0. And now we can calculate the probability that we get a click in the photon detector detects a photon given a quantum state psi as psi m psi. Well, this is our psi, of course. So we can see that in the case that we have this m, we get, so here we get alpha star 0 plus beta star 1. And 0, 1, 0, 0, 0, and then here we get our 0 plus 1, and with alpha. So this is here, then really only the 0, this one, this one, 0 again becomes, so we get alpha star alpha, which is the alpha squared. And a way of saying it is that if we measure a click, this is equivalent in this case to measuring the 0 state, meaning what we actually did now is we measured the sigma z operator, which had the two eigenvalues +1 and -1, where the +1 state corresponded to 0, and the -1 state corresponded to 1. And in this setup, getting this output would be a click, meaning the photon detector saw a photon, while down here, this would be sort of what we call the no clicking. So if you send a photon and you know exactly when to look at your photon detector, you can say that, okay, if I get a click, that corresponds to a sigma z measurement that made a click. And if we did no click, it was a sigma z measurement with the no click event, meaning we measured -1 corresponding to the qubit was in the 1 state. Does this make sense?
So the no click is only valid when you know when to look, right?
Yes, exactly. So, exactly. This scheme only works if you know exactly when to expect your photon. So this is really sort of the downside, even though this is a very simple setup. It has the downside that you need to know when you would expect the photon, which you can time, but if you have a good experiment, but it sort of requires a little bit extra effort. And Timon, I see, is a mind reader because he just asked the next thing that I would do. So let's do one more example for how we can measure in the X basis. So let's first save this. Okay, there's one more question here. That's a very good question. So where does this X matrix come from that it looks on this form? So you can calculate it, but that requires sort of slightly more physics than we will do in this course. But what you essentially need to do is you need to write up sort of the process of going through this polarization filter in terms of how does it change the electromagnetic field. And then you will see that it will change this electric field vector that we had, and you can then infer that, okay, then it must have corresponding to exactly this form of the M vector. And then you can do the detection afterwards, and you can then calculate the probability of getting a click, and you can then combine that again with, and then get this form. Given that we can do it, for the purpose of this course, we will just take this M measurement for granted. But we can just do that, but it can be derived. It's not just we make up as a sort of physical motivation. Good. Then let's go one more example, which relates to the question before in chat, which was part about sigma x. So let's start with the sort of intuitive explanation for what we would expect. So we know that if we are in the y direction, that's a 1. If we are in the x direction, that's 0. So if we want to measure if there's an equal superposition between them, that means that the x direction and the y direction has to be in phase. That would correspond to them being, if you are sort of equal go to x direction and equal to the y direction, then you have to be exactly in a 45-degree angle. While if you would be perfectly out of phase between the two, that would be sort of minus 45-degree angle. So we can expect that that would mean that then we should have theta here to be pi over 4. If we write up the M matrix for that, so pi over 4, that means cosine of that. That's a square root of 2, so square root of 2 squared, that's 1/2. And the same for sine, so what we actually get is 1, 1, 1, 1, like this. Okay. And again, we could in principle now calculate what is psi M psi, so that's the probability we get a click, which is now in this case we get 1/2 here, and then we get alpha star 0 plus beta 1 and 1, 1, 1, alpha 0 plus beta 1. So let's start with just doing over here. So here we then get alpha plus beta 0 plus alpha plus beta 1. And here it's really just the same. And then we can take this with this. So we get 1/2 alpha star alpha plus alpha star beta plus beta star alpha plus beta star. beta, which is equal to 1/2 alpha plus beta, like this. Okay. Did that tell us something? Maybe you remember that this is actually the exact same formula for measuring probability of measuring the state plus if we measure the sigma x operator. But if you don't remember it, we can also try to calculate it slightly different. So what you can remember is that if we take the sigma x operator, right, this is what we have looked at a few times. So we can measure +1, we can measure -1, which corresponds to measuring the plus state, which is the 1/√2, 0 plus 1. And -1 corresponds to measuring the minus state, which is the 1/2, 0 minus 1. So now we can again construct the sort of quote-unquote M operator for the plus state, which is really just a plus like this. And if you do that, you will actually find that this is equal to 1, 1, 1, 1, like this, which is exactly this M operator that we got for this. So a way that you can see that this calculation and this M corresponds to the measurement of sigma x is really that the probability we get at click produces the same M operator as we would get by taking the M operator from sigma x, like this. So to come back to the question that was asked just before, so the way we can now measure sigma x is we essentially just turn our polarization filter 45 degrees. Good. Any questions to this? No questions so far. Then I hope this was clear. And then of course, you can then try to, in principle, find any operator that you're interested in by turning the angle. And specifically, what you will try to do in the exercise later today is trying to construct these S, Q, S, and T operators that we had for the Bell test. So let me do a save on this, and let me do it on. So it's also actually interesting that this way of doing the qubits and the Bell test was actually the very first way that a Bell test was ever done in the world. So here I will put an example of a figure from this research paper from 1982. So what's going on here? So they have this S in the middle, which is what they call S is here for a source. What this is in real life, that's what we would call a nonlinear crystal. Like this. And what this nonlinear crystal does is that if you shine very bright light on it, doesn't need to be very special light, but just shine a lot of light on it. What it can do is it can take a photon with an energy h bar omega, where omega here is the angular frequency of light, and convert that into 2 photons each with energy h bar omega half, meaning that it converts it into 2 photons that has a lower frequency, meaning a longer wavelength. So it sort of converts one frequency of light to another frequency of light. It changes color of the light, so to speak. And it will then emit these 2 photons, always in pairs. But here's the thing. These 2 photons, they have to, when they're emitted, because of 2 times h bar omega half is h bar omega, right? There's always energy conservation. But there also has to be momentum conservation, meaning that if a photon goes, one of them goes in this direction, the other one has to go exactly in the opposite direction with the, and so on. So then every time you do it, there's a small probability that one will go to the detector on slide A, and the other will go to the detector on B. The second thing that is very interesting is that, again, because of, if one of the photons goes like this, because of preservation of momentum, then the other one has to exactly go the other way, opposite direction. Because otherwise there would be sort of temporarily moving energy, electric field going one direction, which would be sort of momentum going one direction. So it has to be cancelled by something going in the other direction. So that's a very intuitive way of seeing that what comes out here actually has to be that we need to have the state that we can write like this. So we have one photon here that could then be, for example, polarized like this. And there's another state here, which is the one going over in this direction, which has to then have opposite polarization. And vice versa. So then if the first one is polarized one way, the other one also has to. So the state that actually comes out of this source of this nonlinear crystal will always be this Bell state. And then this polarization filter that was used in this was actually not a polarizing filter, but actually a polarizing mirror, in the sense that it will let one polarization go through, and the other polarization will be 90-degree rotation of that will be reflected. So, and this is made, even though as Alain Aspect made the drawing like this, you should actually more think of it as there's a mirror sitting like this, and then there's one detector sitting up here, and there's one detector sitting here, where one will get a click if you get the light reflected, and one click if it gets transmitted, and this would then correspond to measuring 0, and this would correspond to measuring 1, and so on. And now what they essentially then did in this experiment was that they did this experiment, and then they had this polarization mirror over B, and they just rotated sort of relative to this polarizing filter in a way such that they could really see they could really measure these operators that was in our Bell inequality. And the exact angles where you get those, you will see in the exercise. So be interested in that. But it's really the same thing they did. And then this was really a very big result. You see this magazine here that published the paper back in 82. Today, if you go to the website, they really write this is a milestone paper on top of it. Because it was really a big thing. And I think it's maybe not very controversial if you want to sort of argue why the Nobel Prize is sometimes a little bit dumb, is that this guy, even though he did this super important experiment that nowadays really changed how we think about physics, he never got the Nobel Prize, which is because back in 82 they thought it was too controversial. But today it's probably we look back and we say sometimes this Nobel Prize committee was maybe not the smartest. But that's just how life works sometimes. Either way, this is a very cool experiment. It really demonstrated that this Bell test is real for the first time. It has some what we call loopholes in the way it's done, which actually took many years to fix those loopholes. And the first time all these so-called loopholes were closed at the same time in an experiment was actually done here in Delft in 2015, and we'll come back to that next hour, so in an hour from now, approximately. Any questions to this experiment? Or to this way of doing quantum experiments in general? No questions? Okay, then I will just go here and I will save. Then I will share my screen and go to my after break slide. So then after the break, we will talk a bit more in detail about how we can generate in other ways entanglements between very separate parties. So you will see here that in principle, as I wrote, these two photons, they are entangled when they travel away from each other because it's a Bell state. But if you want sort of more permanently to have entanglement between two parties that are far away, there's sort of more ways we can do that, and we'll discuss one of those after the break. I'll see you all in around 15 minutes. Great, and welcome back everybody to after the break. Then the next topic that we will talk about is a bit more generic scheme for doing remote entanglement. So in the schemes we talked about for quantum communication and quantum encryption, we would have Alice and Bob, and we would start always to say, okay, they have a qubits each, and those two qubits are entangled in some ways. But how do we get there in the first place? We saw one example by sending the photons, but as was also mentioned in one of the questions by you, it has it's not very practical because then you only have the Bell state in the exact time where the photon comes, which is maybe not really what you want. So here we'll talk about another way of doing it. And the way you will do it is you will, my animation got a little bit braggy, but okay. So the way we will draw it here is just ignore that ball here on the right and just look on the left. So what we will have here is we will have a qubit, and we will sometimes draw it like this. So we'll have two states, the 0 state and the 1 state. And the way we draw it like this is the 1 state has a higher energy than the 0 state, how we imagine qubits. And this thing could really be many different things. I will come back to what it could be, but just think of it as some system where you implement a qubit that has two states, and one of the states has a higher energy than the other. By sort of manipulating this system, you can make the qubit go from the 1 state to the 0 state by emitting this energy difference into the environment in the form of a photon, like this. The way we would write that with sort of our bracket notation is we would say that, okay, in the beginning, we will have the qubits in the 1 state, which is this part here. And we will have the photon in the 0 state, meaning we don't have a photon, right? And I write it like this, and you should really think of it the same way as you would normally think of a 2-qubit state, right? So this is really, to write it more explicitly, we would have the 1 state for the qubits, which has tensor producted with the 0 state for the photon. And then by making this emission process, where you emit the photon by going from the 1 state to 0, this then goes to this state here, where you have 0 state in the qubit and a 1 state photon, which again, what this really means is this tensor product, one photon state. So this is a natural thing to do with qubits when you have them in the lab. And it's a way that you can convert your standing photon or standing qubit state to sort of what we call a flying qubit. Now it becomes a photon. But here's the fun thing. Here's the fun thing that we can do now. So we can do this, but we can actually do it halfway. So instead of going from 0 to 1, you will go sort of halfway there. So you would have sort of your qubit state would be now then an equal superposition of the 1 and the 0 state. 1 over square root of 2, 0 plus 1. But of course, we cannot send out half a photon, right? That's not a thing. The photon is either there or it's not there. So what happens is that we're actually generating this state here, meaning we would have qubit in the 0 with a photon, or at the equal superposition part, the qubit in the 1 and no photon. And this means that we have what we call qubit photon entanglement. And this is really powerful because that means that now you can have your qubit, you can entangle with the photons and the photon far away. And then you can essentially be entangled with whatever is far away, which is pretty cool, right? So that's nice, but it's only sort of half of what we want, because ideally we would like qubit here and qubit here to be entangled. So let's do that and figure a way of how we can do that with these tools. So the way that scheme will then work is that we'll take our usual two participants, so we have Alice and Bob, and they will both have qubits. So Alice will have a qubit in 1, Bob will have a qubit in 1, and then they will do this emit half a photon. And they will send it towards sort of a common place here where the two photons will then meet. Specifically, what will happen is we will have what we'll call a semi-transparent mirror. Sometimes we'll call that a beam splitter, where there's sort of 50% chance that a photon coming here will be reflected, go to this detector. And there's a 50, so there's the photon could go sort of like this. So this will have a 50% chance. Or it could sort of go directly over to this detector over here, which also has 50% chance. And similarly, this could then be reflected like this, or this photon could be go directly through. And then again, that would be a 50-50. And now this whole thing actually will generate entanglement. So why is that? And it requires a little bit of details. So let's just write up the state. So over here we have for Alice, so she will have 1/√2, and then the state where we would have 0 at the qubit and 1 photon, plus 1 at the qubit, let's say QA and photon A for Alice, QA, and then we'll have 0 photon A, like this. This is Alice state, and we can then do sort of this tensor product with Bob's state, which is same, but we should keep track of indices. So that would be 0 Q Bob, 1 photon Bob, plus 1 Q Bob, 0 photon Bob, like this. Or if we now remove all the subscripts and everything, we can just write it in this form here. So we'll get 0 Q A, 1 photon A, 0 Q Bob, 1 photon Bob. And now we just remember that this is the order, so it's QA, photon A, QB, photon B. So then we get plus 0, 1, 1, 0, plus 1, 0, 0, 1, plus and then the final one is 1, 0, 1, 0. Okay. So this is the state of the combined system of Alice and Bob and their 2 photons. And now you can see that they're sort of, by doing this beam splitter here, we will actually lose information about where did the photons come from. So if we get a photon click here, that could have come from Alice, or it could have come from Bob, and vice versa. A click here could have come from Alice, or it could have come from Bob. And there's really no way of knowing. So this detection click would correspond to a photon either from Alice or from Bob. And there's sort of 2 or 3 things that can happen, right? So if we now send these 2 photons, we can have no clicks, so 0 clicks. We can have 1 click, meaning this one clicks or this one clicks, but not the same. Or we can have 2 clicks, right? Which is they both click. If they both click, right, then let's start with that. Then we know that both of them had emitted a photon, so we know we must be in this state. We actually do it with color, so we do 2 clicks. That has to be this state here. The other option is that you can, for example, have 0 click. That would mean actually there was no photon emitted. That corresponds to this state here. And the final option, and that's the one we really care about, is the 1 click state. So because we don't know where the photon came from, we just know that it came from one of the 2 people. It can either be this state here or this state here. So if we do 1 click, the state after that actually becomes 1 over square root of 2. And then we get 0 at qubit A, which is at Alice, and a 1 at qubit Bob, plus the 1 at qubit Alice and 0 at qubit Bob, like this. Which is a Bell state, which is the ones we care about, right? So what we saw here is that by starting with a qubit that can emit a photon, having those 2 photons coming from either Alice or Bob meet at a semi-transparent mirror, and just getting precisely 1 click, not 2 click, not 0 clicks, but 1 click, that actually generates entanglement between Alice and Bob, which is pretty cool. Any questions for this?
I do not fully understand why the blue color, for instance, corresponds with 2 clicks.
Yes, okay, good point. So let's.
Slow.
Yes. Yeah, so let's start with the question here. So the question was, okay, if we have this state here, why does that give 2 clicks? So what we have here is the first state, so that's 0. That's Alice's qubit, it's 0. Then we have 1, which is Alice's photon. Actually, I fucked it up. That's why it was maybe confusing, because I mixed up 2 of the states. I don't know if that was the confusing part, but let me fix that. This was 0, 1, 0, 0. And then we will. So the blue one was actually first state here, which I should have said. Sorry for confusing myself. So here you see one photon, and here's one photon, while the qubit is 0 and the other qubit is 0. So if we, of course, we have to assume that these photons are not lost, right? But assuming they are not lost, they have to go to either one of the detectors. Because of the semi-transparent mirror, we don't know if they go to this detector or the other direct detector, but we know that we get 2 clicks in total. Either one of the detectors clicks 2 times, or they both click 1 each time. And then we just mark the correct. So then the 0 click one, that's the state here. I think I got that right. And then we have the
0 click is the last one, right?
The 0 click is the last one, yes. It was the wrong color. This is the 0 click color. 0 click is this color. And then we have the orange here, which is the 1 click, and this one, which is 1 click, but there's 2 states. So either here it's 0, here it's 1, and here it's 1, and here it's 0. Sorry for the confusion. I hope it's more clear now with the correct color code. So the idea is that we get a click, and to follow up on the question in chat, this click could come from either detector 1, or it can come from detector 2. But it doesn't matter. It just has to, one of them click, the other one no click. That's the sort of key to ensure, and it's very important to do some tests to make sure that the 2 photons arrive at the same time. If they don't arrive at the same time, of course you cannot do it. So there's some calibration to do there, but you don't need to know the exact timing as long as the time is the same, if that makes sense. So such that when you get a click, you know it came from one of them, but you don't know which one. So we have a question if whether the photons were half a photon. Yeah, so the half a photon thing, that was sort of a colloquial way of saying that we have the state here, which is on average half a photon, but you cannot split a photon because it's a photon. So it's the smallest possible amount of energy. It's like an atom of light. So it's there or it's not. So if it's there, then the qubit is in 0. If it's not there, then the qubit is in 1. Does that make sense, Julian? Okay, great. Yes, perfect. Could we place the mirrors in a different position and only use one detector? Not with this way of encoding the qubits. If you want to have less detectors, then you need to do it like this. The other way you could maybe do it is you could essentially take a fiber and then rewire it here, and then combine the 2. That would in principle also work. So there's not fundamentally 2 detectors needed. It's just that the way I drew it here with sort of free traveling lasers, lights with no fibers, then you need 2 detectors. Yes, exactly. It's the semi-transparent mirror, which is the important part. If you read more, if you go into more quantum literature and read, people refer to having this semi-transparent mirror as erasing which way information, meaning we need to find a way to sort of not know where the photons came from, and the semi-transparent mirror is sort of the key operation in that aspect. Good. Then I will clear this drawing. And now move on to the next to show that this was actually scheme was actually used here in Delft, which I alluded to in the previous lecture. So let me walk through what you see here. So maybe you recognize, so this here, this is the aula, right? And then the classroom that we had our first lecture in is here. And then just below that basement over here was Alice. That's our A node. And then you see this is then the TU Delft campus, right? I think our second lecture was then over in this building here. So I think we were sitting over here. And then a little bit up here was another node, that's the B node. And then all the way under was a tunnel where they had a fiber cable connected over to this building here, which I'm actually not sure which building it is, but you can look that up. Such that they essentially just did the scheme we described above. The qubit they used is what is called a NV sender. It's not so important. NV sender, but let me put it in diamond. So what does this mean? So a diamond, that's sort of a crystal of carbon. What you can do is you can take out one of the diamonds and you can put in a nitrogen instead. Now the charge just doesn't add up, so you have to also then next to that nitrogen atom remove one more carbon. You call it when there's an empty space then next to in the crystal structure of diamond, we call that a vacancy. So you have this combination of a nitrogen and a vacancy sitting inside a diamond crystal. And it turns out that that's a very, very good qubit when you do that. You just need a tiny diamond, remove two of your carbon atoms in the diamond crystal and put in, and then nitrogen in one of those three places, which is admittedly a bit hard to do in a controlled way, but we have some good people here in Delft that can do that quite well. So when you do that, then this nitrogen sitting inside of the diamond act as a very nice two-level system that you can use as a qubit. And you can then manipulate that qubit to emit a photon that will then go like over to this beam splitter. And the same you can do over at the B location, where you will then get your photon going out and meet again at this beam splitter or the semi-transparent mirror here. And you have these two detectors exactly as I drew it off. And then it tells you, oh, there was only one click. And then it clicked. And now the key thing is, okay, why do we need to put these things so far apart? And the idea was we wanted to do this Bell test in a way that it closes what is known as the loopholes. What is the loopholes in this context? The loophole is that at some point, Alice makes a decision. Should I measure Q or should I measure R in my system? And Bob makes the decision. Should I measure S or should I measure T? So if we draw sort of, you had a little bit of relativity, right? So you have seen these space-time diagrams. So you will have sort of space on x-axis and you will have time on the y-axis. So there will be sort of an event here, which is where Alice makes a decision to measure in some basis. And then we can make what we call a event horizon for that decision in this, which is a line where you get, which is proportional to the speed of lights. And then at the same time, we also have Bob making a decision. It's Bob making a decision, which will also have some space-time this light cone. But the challenge is that the time it takes from you make this decision until you get your information from here, going from here to the top where you get the output of the qubit, that takes some time. Let's call that tau. So that sits here, tau. And here you will also have tau. So what you need to make sure is that this tau here is long enough. So we need tau to be, tau should be shorter than the delta x times divided by z, such that the information about what Bob decided did not reach Alice in sort of a hypothetical scenario before the measurement of the state in Bob was carried out. So there's the quote-unquote loophole. So that's why you needed to put them so far apart. In this case, 1.3 kilometers apart, meaning you had a few microseconds to figure out what is the state inside of your NV center. So that's the challenge, and that was closing this sort of loophole here was done for the first time in 2016 in this location. So that's the overview of how this scheme really works in real life, the type of qubits you can use, which are these NV centers, and the type of distances where you can really distribute entanglement over. Now they're trying to build exactly the same thing, but having sort of one node here. Then over here you will have sort of Den Haag. And in between we have Rijswijk, right? And now they're trying to essentially do the same thing, but having sort of a photon sent to Rijswijk from Delft, a photon sent to Rijswijk from Den Haag, and then use this beam splitter in Rijswijk to generate entanglement between Delft and Den Haag. And then next step is to do it to Amsterdam and so on. So that's the idea. And that's where we are now trying to build the quantum internet of Netherlands, which is actually the first quantum internet in Europe. There's one more sort of effort in this direction in China. So they have a similar thing between Shanghai and Beijing, and they actually also send up a satellite, and they can do this thing from China to the satellite to another place in China. So they have this part here in a satellite in space, which is pretty cool. So that's sort of where these things are going. So hopefully, and then still within sort of your lifetime, it will become very common to have this type of quantum internet to enhance the security of your internet connection. So, any questions?
So, are the loopholes that there was tried to close here the fact that information can travel faster than light, or to
no,
it's not correct?
Yeah, so the loophole they were trying to close is that what you could think happen is that somehow when Bob makes a decision, of course he doesn't consciously send that decision to Alice, but maybe there's like particles that can move with the speed of light, which is sort of the maximum they can do, that quote unquote listens in to what Bob decided, and then travels as fast as possible, changes the qubit that Alice has, such that Alice's measurement outcome is changed. That's the sort of loophole, which sounds crazy, and it is a little bit crazy because that's not how we think physics work. But in principle, you could explain why we get Bell test to give this larger than 2 value if you assume this sort of conspiracy theories about universe. And you want to sort of eliminate those if you want to really ensure that things are that quantum mechanics is really true.
Okay. So what result would you get at C to prove that this is happening, or to see that these loopholes are not there?
Yeah, exactly. So you need to have this time to be so short that that it's outside of the light cone.
Okay. And then the result would not. Well, they are
exactly.
entangled anyway.
Yeah, exactly. Then even if you are a crazy person and believes in these like conspiracy theories about nature, you would really have to not only break quantum mechanics but also break relativity to explain it.
Okay. Thanks.
Good. Then we are a bit, actually a bit ahead of time, but I think we can just go to our breakout rooms. No, sorry, I wanted to also show the results of the things, just to show that actually they did exactly what we also did here in the lecture. So this is the results they got when they did this experiment back in 2015. So what are these? They use slightly different notation, but just to sort of explain exactly what they are measuring. So what they have here, this is what we would have called the expectation value of Q times S. This is the expectation value of what we would have called R times S. This is the expectation value of R times T. And this final one is the expectation value of Q times T. And you see that now this plus this minus this, you can do the numbers yourself. But if you add them up, you will see that this actually becomes slightly larger than 2. And within the error bars that they indicate, it's also larger than 2. So they broke the Bell inequality. So you see improved quantum mechanics is real. And it's also, I think, remarkable that this exact way of calculating it with these operators, while it was first done in 1982, it really sort of exactly the same way up until today. You actually see these arrows here. It's sort of to indicate the angles of the polarization filter that would correspond to each measurement, which I think is also pretty fun way of illustrating it. Good. Then with that, let's move on to the final part. So I will open the breakout rooms now. We'll take a small break. And then we will, you can just call from help in the breakout rooms, and then Japan and me can join you and answer all your questions. And we will try to also come and visit you in each room. The second thing, since today the questions is a bit shorter, I made it a bit shorter because I got a feeling that some of you were still trying to catch a little bit up. So today the questions are, the problem sheet is a bit short. So hopefully that will allow all of you to catch up. But that also means let's do the last 15 minutes. So at 5:15, we will close the breakout rooms, and then I will just quickly go over the solutions for today's exercises. That's the plan for today. And then next week, we will focus a bit more on the computing aspects of all these quantum stuff. So we will talk about some quantum computing algorithms. How can we calculate things that we couldn't calculate with normal computers? And then in the last lecture, we will talk about the hardware that we use for such quantum computers. So let me now close the slides so I can start.